Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel and today's topic of discussion is gear pumps. Our objective is to examine a common fixed displacement pump known as a gear pump. We'll examine its principle of operation and the internal components that make it function. Recall during the hydraulic pumps lecture, available at the Big Bad Tech channel, we introduced positive displacement pumps, where a positive displacement pump is one characterized by a clear and definite separation between the inlet and outlet ports. The operation of a positive displacement pump can be explained using a sequence of events. First, a positive displacement pump closes an outlet port, opens up an inlet port, and provides a region of increasing volume. For a manual pump, this is the upstroke of the piston. The increasing volume forms a vacuum into which liquid at atmospheric pressure is actively drawn into. This is the suction phase of a pump. Next, the pump seals the inlet port and opens an outlet port, all the while squeezing the entrapped fluid in a region of decreasing volume. This is the compression and exhaust phase of a positive displacement pump. For a manual pump, this is the downstroke of the piston. Next, the outlet port is sealed and the inlet port is open, and the process repeats itself over and over. The completion of one full open inlet, closed outlet suction and closed inlet, open outlet compression and exhaust is known as a cycle of a pump. For rotary pumps, one complete cycle of a pump is ordinarily one complete revolution of the drive shaft. Positive displacement pumps use close-fitting components and must properly filter and condition fluid to be pumped to predetermined cleanliness standards if they are to perform reliably. Particulate contaminants may progressively abrade close-fitting components, leading to a loss of lubrication and sealing ability, as well as hinder efficient movement of the dynamically moving surfaces. Additionally, heat-degraded oil forms a sticky resinous byproduct known as varnish that can plug ports and glue ordinarily moving components together. The fluid filtration and conditioning lecture, available at the Big Bad Tech channel, discusses these effects and the means of mitigating them. In summary, positive displacement pumps have a suction phase that actively draws in fluid and a clear and definite separation between inlet and outlet ports. Positive displacement pumps are for applications necessitating high pressure, like hydraulic systems. Three types of positive displacement pumps are commonly employed in hydraulic systems: gear pumps, vane pumps, and piston pumps. Pumps, regardless of their type, can be classified as fixed or variable displacement pumps. Fixed displacement pump, as the name implies, is incapable of varying displacement per revolution. A variable displacement pump, in contrast, uses movable internal components to selectively increase or decrease displacement per revolution as required. Gear pumps use a pair of equally sized meshing gears to provide pressurized flow to a hydraulic system. All gear pumps are fixed displacement pumps. Vane pumps can either be fixed or variable displacement pumps depending upon construction. A vane pump uses a slotted rotor and extendable vanes that scrape the inside of a cam ring. A fixed displacement vane pump keeps the relationship between the rotor and cam ring constant, whereas a variable displacement vane pump varies the position of the cam ring or rotor to vary displacement per revolution. Piston pumps can either be fixed or variable displacement pumps depending upon construction. A piston pump uses an angled plate to position pistons inside a rotating piston block. A fixed displacement piston pump keeps the angle constant, whereas a variable displacement piston pump varies the angle to vary displacement per revolution. The intention of this lecture is to examine the internal construction and discuss the principle of operation on gear pumps only. Later lectures will examine vane and piston pumps. All gear pumps are fixed displacement pumps in that the quantity of fluid introduced per revolution of the drive shaft cannot be modified by moving internal components. Flow rate is a measure of volume per unit time, and flow rate is the principal factor that influences actuator speed in a fluid power system. Flow rate is the product of displacement per revolution times rotational speed. This calculation ordinarily necessitates a unit conversion, since displacement is customarily expressed in units of cubic inches per revolution, and flow rate is customarily expressed in units of gallons per minute. Displacement is often referred to on a pump datasheet as CIR, or cubic inches per revolution. Since all gear pumps are fixed displacement pumps, this relationship suggests that the only way flow rate can be varied is to increase or decrease rotational speed using a variable speed prime mover, the classic example being an electric motor with a motor drive. As discussed in the hydraulic pumps lecture, accurate flow rate calculations must take into account two important factors at increasing pressures. 1. Decreased displacement per revolution due to increased leakage, and 2. Decreased rotational speed of the prime mover due to increased torque requirements. A graph of volumetric efficiency, or flow rate at different pressure requirements provided by the pump manufacturer, would allow a technician to predict these influences. However, if we neglect these pressure-induced complications, given a gear pump with a fixed displacement of exactly 0.5 cubic inches per revolution, driven at exactly 1,800 RPM, we would expect it to produce a flow rate of 900 cubic inches per minute, or roughly 3.9 gallons per minute. Gear pumps are simple, inexpensive pumps, and because of these factors are extremely popular and reliable for most hydraulic applications. Gear pumps can either be external, lobe, internal, or gear rotor type. However, the external gear pump is the most popular configuration and the focus of this lecture. Those interested in lobe, internal, or gear rotor type gear pumps are encouraged to seek guidance elsewhere because I am not going to cover them because you are not going to run into them. On the rare occasion you do run into them, do not let me know because I don't care. I really don't. With an ounce of determination, you should be able to figure out how these alternative gear pump configurations execute the suction and compression and exhaust sequences of positive displacement pumps. External gear pumps are characterized by a pair of equally sized intermeshing externally toothed gears. One gear is the active drive gear. The other is the passive driven gear. Besides the term drive and driven, this pair can alternatively be called master and slave, or drive and idler, among other manufacturer-specific terminology. As the title implies, the drive gear is the one actively turned by the prime mover. The drive gear is identified by being the one with a key or keyway to which a shaft can be attached. Alternatively, sometimes a drive shaft is permanently affixed to the drive gear. The prime mover, be it an electric motor or internal combustion engine, rotates the shaft, which in turn rotates the drive gear. Note, very rarely is the prime mover directly attached to the pump shaft, but rather uses a coupling intermediary. The coupling compensates for misalignment and allows a technician to take the pair apart for maintenance, inspection, or repair purposes. The driven gear, in contrast, is passively turned in the opposite direction by the meshed teeth of the drive gear. When the drive gear is rotated counterclockwise, the driven gear passively rotates clockwise. In contrast, when the drive gear is actively rotated clockwise, the driven gear passively spins counterclockwise. The drive and driven gear live inside a housing or body with two ports. Given the drive gear is actively rotated clockwise and the driven gear passively turns counterclockwise, this means the bottom port creates a region of increasing volume as the teeth unmesh. This port would therefore be the inlet and be performing the suction phase of a positive displacement pump. Oil trapped between the teeth and the housing is then brought around each gear and deposited in a region of decreasing volume as the gear teeth mesh together. This port would therefore be the outlet and be performing the compression and exhaust phase of a positive displacement pump. In summary, when this drive gear is actively rotated clockwise and the driven gear passively turns counterclockwise, the bottom port is the inlet and the top port is the outlet. This tends to be a point of confusion for most people since they incorrectly assume liquid is pulled in the opposite direction through the meshing teeth like a piece of paper through rollers on a copier or a printer. This is incorrect because liquid is an incompressible phase of matter. Liquid is sucked into the system by the unmeshing teeth and then brought around the gears and squeezed into the system by the meshing teeth. This behavior is perhaps best illustrated using an animated clip. Notice how the unmeshing gears create a region of increasing volume which fluid is actively being drawn into at the inlet port. Oil, symbolized by the bubbles, is trapped between the teeth and the housing and brought around each gear. The meshing gears create a region of decreasing volume, which pressurized fluid is being actively pushed into the system. If the prime mover were to switch direction, directional flow would also reverse. Note when the drive gear actively turns counterclockwise, the driven gear passively turns clockwise. This means the top port creates a region of increasing volume as the gear teeth unmesh. Oil trapped between the teeth and the housing is then brought around each gear and deposited in a region of decreasing volume as the gear teeth mesh together. In summary, when the drive gear is rotated in the opposite direction, the top port is now the inlet and the bottom port is the outlet. Note, not all gear pumps are designed to be driven in reverse and are ordinarily unidirectional. We'll examine the details behind this in a moment. You should be able to determine direction of flow and/or direction of rotation for one or both gears given a diagram of a gear pump in different orientations. Just saying, this might make an excellent quiz question, and only your lazy lab partner could blow something this easy. That's really all there is to the internal construction and basic operation of an external gear pump. Let's disassemble some representative examples of gear pumps and see if we can identify some of the constituent parts. Here's the internal workings of an extremely simple gear pump. There's really only two moving parts, the drive and the driven gear. For this reason, gear pumps have a reputation of being reliable, robust, and inexpensive. However, not exactly the most mechanically efficient pump, nor suited for super high pressure applications. When disassembled, note the idler gear spins on an axis internal to the housing, and the drive gear is permanently affixed to the drive shaft. When reassembled and the drive gear is actively rotated by the prime mover, the gear pump performs as we expect. The unmeshing gears at the inlet create a region of increasing volume, which fluid is actively drawn into. Oil would be trapped between the teeth and the housing and brought around each gear. The meshing gears at the outlet create a region of decreasing volume, which pressurized fluid is actively pushed into the system. In addition to the housing and the paired drive and driven gears, gear pumps have both dynamic and static seals. The drive shaft would form a dynamic seal with that of the housing, since they move relative to one another. In contrast, the housing would form a static seal between the two non-moving halves with the use of a gasket or an O-ring. These seals might be the only parts that really require routine maintenance if the pump is operated inside the recommended range with properly filtered and conditioned fluid.